Morning, everyone. I'm going to wrap up node voltage analysis today and then introduce the topic of mesh current analysis. That is the last analysis technique that we'll look at in this class. After we finish mesh current analysis, the two topics remaining, superposition principle and Thevenin and Norton theorems. Both of those utilize the analysis techniques that we have already learned previously. Okay. But the analysis technique, as far as analysis technique goes, this is the last one, mesh current analysis. So I probably will not be able to finish mesh current analysis today, but since I'm introducing the topic today, please go online, take a look at the homework, open it up. You might want to look at the tutorials, which are extra credit. Okay, so look at those. We'll get into the theory of mesh current analysis. Won't be able to get in the example probably. Yes. So I was gonna move it to Sunday. Yeah. Let's see, because both of those only have like 3 problems each. So node voltage analysis and mesh current analysis both have 3 problems each. Oh, so one of the other things I received in a feedback comment was that the tutorials and video solutions had some extra material in there. That's the point, because it's extra work, there is extra credit to it. So students can do it if they wish to. If you recall, on my syllabus and on the first day of class, I said this is a multimodal, meaning students can take this online, offline, asynchronous, or in person, and then multi-level class. Multi-level simply means you can learn stuff that is not part of the normal syllabus, and that's why it's extra credit. Okay, so the homework has extra credit problems, practice problems that are beyond the scope of the normal syllabus. So if a student wishes to go beyond, what the class can, what I can teach in class, then feel free to do so. It's an extra work, and that's why I award extra credit. So if you come across something in the tutorials that is not covered in class, that is the reason why. Okay. Hope that answers the questions. Any other questions before I proceed? Okay. All right. Share. I always forget to switch it to the screen. Okay. And this should be 0.2. So we stopped right here on this problem. The answer to this, if you remember or you recall in class, I think a student did solve this on their calculators and obtain 11 and 47. Okay. And there's also a point raised why I take like 3 or 4 decimal places, 3 or 4 significant figures. Well, if I solve it using those numbers, the ones that I have in the board right here, these, instead of rounding up to like 1.2 or 0.6, what I actually get is minus 13 point something, and here it's minus 52.86. I think this is minus 13.57. So there is a difference in the numbers. When you're solving this for class, it does not matter, as long as the methods are correct, and if your numbers are this close, I will give full points. Okay. But as a real life engineer, when you go work for the industry and you're designing a system, then it makes a difference. Oh, 13.57 and 52.86. Okay, and then one final point about this was, once you have the node voltages, I believe I mentioned this, but I'll repeat it again. Once you have the node voltages, you can find the resistor voltage VR1, VR23, and VR4. You simply take this and plug the node voltages in that equation, you get VR1. Same thing here. VR23 is VA minus VB. You plug in the values for VA and VB, you obtain the resistor voltage. Once you have the resistor voltage, you can find the resistor currents using Ohm's law. Yes. That would be positive. That is based on the assumption of the currents. So we assume current directions going left to right. That means plus is on the left, minus is on the right. So I'm making an assumption at the beginning of my problem or my beginning of my analysis that point A is going to be higher than B. Yeah. So all of those signs, they all come from the assumptions we make at the beginning. Okay, any questions?
Professor Kraft,
Yes.
from the homework, what's the difference between solving for the summation of current leaving the node and the summation of current going into the node?
That's just simple KCL. So basically, all the currents entering a junction, all the currents entering a node have to equal all the currents leaving a junction. And so if you remember or recall the steps, after setting up the problem, we generate equations by writing a KCL equation at every node. And that's what it refers to. There was, yeah. Mm-hmm. Yes, we can. Because it's based on our assumption, right? So the values of these variables do not matter. We simply plug in the values as they are. So VA and VB were both negative. So typically I don't do this, but let's go ahead and solve this. So VR1 is VA minus VC. VC is equal to 0 because it's a reference node. So VR1, voltage across resistor R1, is simply VA, right? And VA is, we already obtained, minus 13.57 volts. Okay, so voltage across resistor R1, meaning measured from this point and this point, because we marked our polarity as plus and minus. So that minus sign is referring to this polarity. It's referring to that polarity. If we had assumed our current going in the opposite direction, if we had assumed our current going in this direction, then the bottom connection would be positive, the top would be negative, and our answer would have been plus 13.57. Does everybody understand that? We obtain a negative value for both node voltages just because of our assumptions at the beginning of our analysis. Okay, if we chose, and I can illustrate with another point. So we have 3 points, right? A, B, and C. 3 nodes, A, B, and C. C is given as 0, the other 2 are negative, meaning VA and VB are both lower in value than node C. Does everybody agree on that? Node C is a reference point, so node C is 0 volts. Where is VA? The second line or the third line? Look at the values. Second line, still hesitant. It's just pure math number, right? So VA is here. It says minus 13.57 volts. And VB is here. Obviously, this is not to scale. 52, minus 52. Now, let's just say another student chose node A as their reference. Okay. Instead of choosing node C at the bottom, if you choose node A, which is right here, as your reference, you can solve this problem using those equations So if A is reference, then VA is 0 volts. What would be VC? The difference between A and C doesn't change. VA is below VC. So VA is 0, VC is above by 13.57. So in that case, your answer would still be correct, but it'll be plus 13.57. Again, voltage is the difference in potential between any 2 points. The actual value does not matter. This could be like 100, then VC would be 113.57. So at the beginning of our analysis, if we choose A as a reference, VA is 0, VC would be plus 13.57, and VB would simply be what? The difference between A and B. So about 39 volts. Does that make sense? Kind of. You can choose B as a reference. So if you choose B as your reference, then VB would be 0, VA would be about 39, and VC would be plus 52. Your answers would still be correct because of the assumptions you make and the markings on the circuit schematic that you show me. You could also choose a different direction for your current. Instead of current going this way, you could simply choose currents going up. Yes. No, that doesn't, because the polarities come after. Sorry to interrupt you, but the polarities come after we make the assumptions for the current. So if you assume the current going up, if I'm assuming current going up, then I assign a polarity for the voltage. So point of entry would be plus. Here, this would be minus. And that's why our equations and our answers will always be correct, because the voltage polarity that we assign here is based off of the direction of the current that we chose, which is coming down from the top. If we choose going up, then the voltage polarity is positive at the bottom. Again, current always flows from high to low, plus to minus. So point of entry is always plus, point of exit is minus. Yes. Yes. Yeah. Question was reference node, and the answer is yes. You can choose any node as your reference node. Once you choose it as a reference node, that automatically is assigned a value of 0 volts, but only for that analysis. Again, as I said, in this example, I chose C as the reference node, so VC was 0. If I choose A as my reference node, VA would be 0, and so on and so forth. Then you choose or assume a current direction, and once you assume a current direction, then you can assign voltage polarity. So again, do not skip steps. Take it one step at a time, okay? At the beginning, take your time. Once you are adept at solving these, then you can, skip steps if you wish, but do not skip steps. All right. Any other questions? All right, good discussion. So once you have VR1, you can apply Ohm's law. Again, as I said, typically I don't solve these, but since we're already here, I can write IR1 is simply VR1 divided by R1 from Ohm's law. This would simply be minus 13.57 and divided by what? R1 is 1000. Easy enough. So this gives me minus 13.57 milliamps. Again, do not forget your unit prefix. Okay. If you forget the M in there, the answer is totally incorrect. 13 amps versus 13 milliamps. So now I obtained a negative, simply means my assumed current direction is opposite of the actual one. It doesn't mean that my answer is incorrect. Again, I will look at the current direction that you have chosen, and then I'll look at your answer. The magnitude, of course, has to be correct. If the magnitude is incorrect, then your answer, there's an error in your calculation somewhere. But if you have plus 13 with the combination of the assumed current direction, your answer would receive full points. Yes. So if a current direction is already given in the problem, then it makes a difference. See, in this case, in this example, a current direction is not given to us. There are no current directions given to us. If a current direction is given, if there's a current source in there and a current direction is given, then yes, we have to use that current direction.
In this diagram, the plus and minuses of the resistors are what gives us current.
No. The current direction gives us the plus and minus. Those are current sources. No, that is giving us current direction. It's going up. The assumed direction is only for the resistors. So here, I'm assuming the current goes this way. Here, I'm assuming it's going down. But because this is 50 milliamps and this is 10 milliamps, logic would state that this is a larger current, so it's probably going to force current going up rather than going down. I chose going down specifically to make a point that even if we receive a negative answer, it does not mean that our answer is incorrect. You can solve this entire problem with it going up, and you receive positive answers. All right, let's see what else was there. VR23 and IR23. Basically, you can find the same currents going through here and through here the exact same way. Again, it's Ohm's law. Since we have done that before, I do not do that for every example. But you plug in the node voltages, you find the resistor voltages, and then you find the current. So the question might ask you to find just one specific current using node voltage analysis, and you just find that one current. Here in this case, it just says solve for all branch currents. You would find all resistor voltages and all resistor currents. Okay. All right. So one last topic about node voltage analysis is if you have more than one, well, if you have one or more than one voltage source. Now, for node voltage analysis, we write KCL equations, right? If you're writing KCL equations, we want to describe the currents flowing in each branch. And we use the node voltages to describe each of those resistor currents. But if it's a voltage source in there, we cannot write a KCL equation going through that voltage source, right? So in that case, what we do is we combine that voltage source and kind of short it out. Meaning, we do this. In this example, what I would do is this is R3. I would simply remove the voltage source and place a short in its place. And let's see. This is R4. And so I would make a single node out of these 2 points. So either end of the voltage source is now connected together. And so then I can write a KCL equation. So you simply remove that voltage source, place a short circuit in its place, basically shorting out the 2 points of that voltage source. And you just combine it together. And that's it. So now you can write a KCL equation. I can have current R3 going this way, and if I had in the, depending on what current direction I've chosen, I would have both of them then going this way. So if this was if this was a branch of the circuit, I cannot assign a current here. It would just be an extra variable, and that variable would have no answer. I would not be able to find anything for that variable. I could label it IS1 and IS2, and I cannot describe IS in terms of the node voltages. So we simply short it out and write a KCL equation. One other thing we can do is, if you have two sources in a circuit, you choose the bottom one as your reference node, then the other one gives you an answer, right? So if this bottom node is reference, that one is 0 volts. And because the power supply is connected with a plus at the bottom, this would automatically give us a value of minus 15 volts. Okay, minus 15. Make sense to everyone? Right? That's the first point I made in the previous schematic. Then with this other source, like a 10-volt source right here, I can short it out. But before I do that, I can generate an extra equation, a relationship between nodes V1 and V2. Because there is a power supply connected there, I can simply write, positive end is of course higher, I can write V2 minus V1 is equal to 10. Similar to this voltage source right here, I can write an extra equation. So I can write V2 minus V1 is equal to 10 volts. And I can describe either V2 in terms of V1 or V1 in terms of V2. So even if I don't have a KCL equation, I still have this. Be V1 plus 10 or V1 is equal to V2 minus 10. And then when I have my equations at the end, these two variables, since they can be described in terms of each other, you can pick and choose which one you wish to use, and you can eliminate one variable. Make sense? Right? So after you do this, and then you can combine it as a supernode. So you do this, then combine as a supernode. Yes. No, for a supply, it always goes from minus to plus. For a supply, it always goes from minus to plus because it's supplying. That's the passive reference configuration. Current always goes from plus to minus for all components, but if it's a supply, it always goes from minus to plus. Remember, power is negative for a supply because it goes from minus to plus. We put a mathematical negative sign, otherwise the equations would never work. Important point about supernode. You do not short out all of your voltage sources, only the one extra ones. You keep the main one alone, and then you short out the other ones. Okay? You do not apply supernode to each and every source in there. There is a way to do that, but you shouldn't. Well, I mean, main as in like whichever one you pick as your reference node. You can choose 2 as your reference node. You can choose 1 as your reference node, and then you'd combine this one into a supernode if you wish. Yeah. You can combine all of them into a supernode. It's fine. But I always suggest to students, not to do that because it just complicates things, and students often end up making errors. So even if they know the right techniques and they apply everything correctly, because they short up the power supply, they end up making errors. So again, it's a concept that's very useful. All you're doing is you're shorting out, you're taking out the power supply, and you're placing a voltage, you take out the voltage source and you place a short circuit along that path. You're just connecting a wire along that path. That's all you're doing. And then you can write KCL equations. All right, any questions? Any questions at all? I think one of the homework problems does have two sources or two voltage sources, if I'm not mistaken. Yes. If it was me, I would choose, what would I choose? It actually doesn't matter. I'm trying to remember. I think I chose V2 as my reference node. So I chose 2 as reference. And the reason is, I'm trying to think. Was it V2? No, I solved it using 1 and 2, both. So I've chosen 2 and I've chosen 1. I've solved this multiple ways. So if 2 is my reference, then V1 is minus 10 volts. If 1 is a reference, then V2 is plus 10 volts. In either case, there is nothing linking this 10 volt power supply and the 15 volt power supply. If they were linked together, then it would make sense to choose that node. No matter which node we choose, we would obtain value for one end or the other end of that voltage supply, voltage source, and the other one we would have to apply a super node. Yes. Sorry. Yes. We'll just do that as a super node. So in that case, if we name this bottom node as 4, I would say V4 minus V3 is plus 15 volts. Instead of V1 and V2, it would be V3 and V4 relationship. Yes. That's just for theoretical calculation purposes. Yes, because if you think about it, there is a current that's coming through here. Some of it's going to go down here. Some of it might be going here. We don't know yet. We can assume it's going this way. So if you want to write a KCL equation for this branch, the current is not going to change, whether the voltage source is present or not, for calculation purposes, only for calculation purposes, okay? So the current is going through here, but I cannot describe that current in terms of my node voltages. For a resistor, I can say V3 minus V2 divided by R3 is equal to the current flowing through R3. But what do I do for here? I cannot describe it using Ohm's law. So for this analysis technique, this is just another additional step that we take to write equations. We are not changing the actual circuit. We're just making certain assumptions to analyze. If there's a need, yes, we can. But that doesn't change the fact that this node still remains at minus 15. The values for that node still remain the same. Again, that's a very important question, and that question brings up a very important point. If you're writing equations and you draw a super node, it is not changing your circuit, okay? The super node actually comes from the fact that if you write a KCL expression, it eliminates the current flowing through that power supply. And I can show it to you right now. Let's take it a step further. So there is a reason why we can do that super node thingy. So typically we don't do this for non-EE classes. We simply explain the concept of super node, but there is a reason. It has a basis right here. So This is R1. This is R3. This is R4. And that's my junction, right? So let's make an assumption. Currents through R1 and R3 are coming in this direction. So R1, I'm going to say IR1. R3 is IR3. And this is R4. Let's assume this also coming down. So this is IR4. And I'm going to call this as IS. Okay, IS. So current coming down. So if I apply a KCL equation at this node, and let's call this node X, and let's call this bottom node as Y. If I apply KCL at, again, this is not part of the class, so it's not something that you have to do. This is how a super node, principle can be applied. That's the point of this. So KCL at X gives me IR1 plus IR3 is equal to IS, right? And if I apply a KCL at Y, what do I get? Again, this is nothing too complicated. I get IS entering, and then what do we have? IR, oh, this also needs to have a current. So this would be R2. So IR2. So I would have two currents entering, IS plus IR4 is equal to IR2. Now I would rearrange both equations in terms of IS. If A equals Z and B equals Z, I can write A equals B, right? And so I would express both equations for IS. The first one is already in terms of IS. The second one would be IS is equal to IR2 minus IR4. Therefore, I can write from both equations that IR1 plus IR3 equals IR2 minus IR4, which is the equation you would get when you apply a supernode. Let's take a pause while you write it down and think over that. All I did was I applied KCL at both ends of that voltage source. I assigned a random variable to the current flowing through that voltage source, which is IS. And then I obtained two equations by applying two KCL equations at each end of that voltage source. Then rearrange the terms, you get an expression for that current. You equate both of them, and that equation, which is this equation right here, is the equation that you would obtain if you combine this 15-volt source as a supernode. It's the exact same thing. So this is a supernode. I have IR, what is this? IR4, IR2, and this is IS. This is R3. And of course, we also have IR1 coming from the top. So if you apply an KCL equation around this node right here at the bottom, you would obtain this equation. Does everybody see that? Yes. So again, yes. Question. Mhm. It allows us to skip all of those steps. So all of this that I did right here, it allows us to skip all of those. As I said, so it has a basis for doing it because it's the exact same thing. But again, if it's a EE class, we go in depth and we explain why things are the way they are. But as non-EE engineers, you would learn these tools. It's kind of like, as I said, it's not, you learn these tools, but it's more important for you to know how to use them rather than to know how they were developed, if it makes sense. Knowing is a good thing, obviously. I wouldn't say that it's not a bad thing, but again, considering the scope of the class and how much time we have available to us, we do not go in depth into every, you know, every derivation. So supernode is kind of like a shortcut, if you will. Yes. No, no, IR1 is also coming from the top. So it's IR3 plus IR1. That becomes IS. Now, so you're talking about this one. So we don't, this was just illustrating the point that IS would be flowing through here. But if you're doing a supernode, then there's no need for IS. Actually, that's confusing. So let me take it out. So if you apply KCL here, I simply have IR1, IR3 entering. This is all one node, right? From the top, it's all one node. So I have IR1, IR3 entering, I have IR4 entering, and then IR2 leaving. So my KCL equation would be IR2 is equal to IR4 plus IR3 plus IR1, which is what I have here. IR2 is equal to IR1 plus IR3 plus IR4. That makes sense, right? Yes. Yes, it doesn't. Yeah. It's just, it's, as I said, it's the simplest one-line answer would be a supernode is a shortcut. So like voltage division principle and current division principle, they are shortcuts so that we don't have to apply Ohm's law. We can skip one or two steps if you apply voltage and current division. The supernode, and then we'll have a super mesh, is they are shortcuts. The shortcuts are derived from the same thing, same equations. So again, efficiency purposes. All right, we good? Okay, so let's talk about mesh current analysis. Mesh current analysis, this gets even more, well, I don't want to scare students, but it's a little bit more confusing than node voltage. So if you look at the circuit, I said if you can look at a circuit schematic and you can identify loops and you can identify meshes. A mesh is a simple loop. So meshes are easier to identify than an electrical loop. In this case, mesh 1, mesh 2, and mesh 3, right? So I would say this is M1, M2, M3. Only 3 meshes in the circuit, very easy to identify. But an electrical loop is any closed path around the circuit. You start at one point and you take a path around all the components and you come back to that exact same point. That is an electrical loop. So in this case, in this circuit, that's one loop, that's 2, that's 3, that's 4. What else? 5 and 6. 6 loops. Anyone see anything more? 1, 2, 3. Yes. This is the outer loop. And this is the smaller one, 7. This combines all 3. And this combines 1 plus 2. This is 1 plus 3. This is 3 plus 2. And let's see, 3 I got, 1, 2, 3. I think that's it, 7. Does anyone see any other loops? Yes. The outer loop, right? That's this one, 6. Just the top one would be 3. Is that the one that you're saying? No, the top one is already here. Counted as 3. Yeah. So there are 7 electrical loops. Again, it doesn't matter for the purposes of analysis. So loops are a little difficult to identify, but meshes are easy. So if you have 3 meshes in there, the first thing to note about mesh currents is that they are purely hypothetical. They are total assumptions on our part, exist only on paper for us to be able to solve for the circuit and write equations. That's it. Yes. So mesh is defined as a simple loop that does not contain any other loop inside it. So if you look at, let's say, number 4 or number 5, number 7 or number 6, all of these have other meshes inside it. So a mesh is a simple loop. Sorry, the 4, 5, 6, 7 electrical loops have other smaller loops inside it. So if it doesn't contain any other electrical loop inside it, then it's a mesh. As I said, mesh is easy because our brains can directly visualize different sections of a circuit schematic. So as I was saying, mesh currents are purely hypothetical, purely theoretical. They do not exist in real life. Okay? They do not exist in real life. So we assume, we identify the meshes, we assign a mesh current to it, and we have to assign a direction to that mesh current. Typically, I always choose clockwise. But again, as with our branch current directions, the assumptions, we can make any direction we want. You can choose to go counterclockwise, which is absolutely fine. But I always choose clockwise. So once I have my clockwise direction for the current, now, remember, node voltage analysis, I said we apply Kirchhoff's current law, KCL, to write our equations. So it's mesh current analysis. Any guesses on what we use? KVL. So mesh current analysis, use KVL to write equations. And the reason is a mesh current is going to cause a voltage drop across each of these resistances. So you have a voltage across each resistor due to these mesh currents, and then you apply KVL to add those up. And we'll see how. So first thing here is, let's look at mesh 1. Mesh 1. This is R2, VA. This is R3, but I'm going to write R3 here. And then, of course, I have my mesh current. I1. So Passive reference configuration. If current enters the resistor from the left, what is the polarity? Plus or minus? Plus, right? Point of entry is plus. So I1 is going to cause a voltage drop across R2 with this polarity. Yeah. Plus, minus R2. And I will simply call this VR2. Same thing for R3. I1 is going to cause a voltage drop across R3, and point of entry is plus, point of exit is minus, and that is going to be VR3. However, this is a shared mesh. R3 is common to both M1 and M2. And when you have that, you have to account for the current that is flowing, the mesh current that is flowing through R3. If I look at I2 is also clockwise, and it flows in the opposite direction. That causes a, yes. Yes, that is correct. Good point. Let's see. I3, so the point being made was we have to account for I3 also, and that is absolutely correct. I overlooked that. We have to account for I3. So in this case, I'm going to change this. I have plus and minus here, and plus and minus here, and then plus and minus here. And the reason I emphasize on the point saying that mesh currents are hypothetical, because you cannot have two currents in a single branch of circuit. It's physically impossible. Okay, current only flows because there is a potential difference at either end, meaning one point or one end of that junction, one end of that component or one end of the resistor is at a higher potential than the other end. So if this is higher, current goes from here high to low. If this point is higher, then current goes from this point to the lower point. So it's not possible, it's not physically possible to have two currents flowing in the opposite direction in the same branch. Okay, it's not possible to have two currents, period, more than one current in any single branch. So mesh currents are, again, hypothetical, they are not real. Okay, so this is I3. It causes a voltage drop in the opposite direction. So if I was going to write an expression for KVL, and I write it in this direction, KVL, I would say I have VA minus VA plus VR2 I1 minus VR2 I3 plus VR3 due to I1 and then minus VR3 due to I2. Let's take a pause while you think over it. Again, as with node voltage analysis, this is very important. And I think we are out of time. So I'm going to end on this note right here. Review this much, where I said we have to account for both mesh currents if it's in a shared mesh, shared branch of the circuit. And then we have two different voltages in there. The first one is due to the first current, KVL direction. And the second one is minus because it drops opposite polarity. So we'll end class here today. Open up mesh current analysis homework. Take a look at it. It won't be due until after I get done with the example, which won't be until like Monday or Wednesday. There will be a quiz on Monday. The topic will be node voltage analysis. The announcement will be posted on Canvas. Okay. All right. I wish you all a good weekend. I'll be in my office. If you have questions, I'll be available right now also. But let me end class here first, and then I can answer your questions.